All right, guys, I want to take care of a few administrative things first. First of all, I put a practice test up. I sent an email out about it. Has everybody gotten a chance to look at it? How did y'all feel about it? Easy, difficult? About what you'd expect? All right. This is just a sample of what you might expect. So there were a few topics that I did put on this. I think I mentioned that in the email. Like, for example, I think really the only topic was, what was it I said? Standards of measurement. Like, what's the standard for distance? What's the standard for mass? And what's the standard for time? I don't think I had any questions about that, but you could see some questions like that. All right, this is just a sample for you. I'm not going to give this to you every quiz. I just wanted to give you an idea of what to expect. All right? Do you feel like you know what to expect for the quiz, which is coming up on Thursday? Well, it's not going to be exactly like this, right? It's not going to be these questions, but it will be laid out in this format. And some of the questions might be very, very similar, okay? You'll have a few simple calculations. We're going to do some of those today, but they're going to be very simple, and we'll do lots of examples in class, okay? I know that people are often afraid of taking physics, but I don't want that for y'all. I mean, I don't want you to schlep off the course either, but I don't want you to be afraid of it. Are you afraid? Don't be afraid. All right. The answers are given. If you have questions about this, you can come see me. I don't think we need to go over it in class. Most of them were fairly straightforward. But if you have questions, then come see me, okay? Also, I've had a number of questions about the project. Now this project, the proposal, if I'm not mistaken, is due 2 weeks from today. Let me check the date on that. Yeah, the proposal is due on Thursday, February 14th. What I want is a paragraph describing what you intend to do for the project. I want to take a few minutes today, about 5 minutes, and I want y'all to just sort of brainstorm some ideas, and then we'll share ideas among one another, okay? Just sort of discuss them. We'll just take about 5-7 minutes to do this. All right? So in short, I sort of laid out the types of projects that you can do. Faith, did you have Astronomy 101? Did you have Astronomy 101? Yeah, so I ripped this off from my wife. I don't know if you noticed that. Did you notice that? But I think it's a good idea because sometimes students aren't very good test takers, and I understand that. So this is meant as a way for those of you who aren't very good test takers to improve your grade in the class without relying too heavily on tests. And I think it'd be kind of fun. Did you have fun doing it, Astronomy 101? You can tell me the truth. Really? Okay. So you can. I just sort of have 4 different types of projects that you can do. You can do a written document, a whole array of things. You can do a media topic, film or documentary. You can do a painting. You can do a website, a video game, a sculpture or model of something. You can do a presentation, an in-class presentation, video tutorial. You can present to a community or school group. You can have other ideas as well. So something that you want to come up with on your own. May I ask you, Faith, what you did last semester? Oh, you have it this semester. Okay. Well, students, in my wife's Astronomy 101 class, they did this. And she had a whole array of things. Like one student did a astronomy trivial pursuit where he made up a game. It had a game board and the pieces and all that. And he had questions like you have in Trivial Pursuit with different topics. All right. One student did a sculpture of a star-forming region. Now yours obviously would be related to physics, in particular for allied health, be it in athletic training or whatever you like to do. All right, something that's related to this course. Let's see, some students did paintings, some students did papers, some students did videos, a whole array of things. And it's really up to you. And that's why the description is fairly broad, because it's really your choice, and I want it to be your choice. All right? So let's take a few minutes and either with a few other people or by yourself if you prefer, just jot down a few ideas, okay? I have 9:07, so we'll go to about 9:12 or 9:11. All right, so just take about 4 minutes and just jot down a few ideas that you might have. Now I'm going to pull up the syllabus, which has all the chapters that we'll be covering, and so that you'll know the topics, because the project has to be related to the course somewhat. All right, so these are the topics that we're covering. motion, force, work, energy, power, temperature, fluids, pressures and fluids, waves, electricity, light, vision. Put your pen to paper. Just start jotting down ideas, however crazy they might be. Just a couple more minutes. I'm going to ask you to share some of your ideas. Morning, Danielle. We're taking a very important test right now. Sorry you missed it. No, I'm joking. We're not. Danielle, we're thinking of ideas for the project. So if you have any for the project, maybe you can work in groups for the project, up to 3 or 4. 3, I think I said. Just one more minute. Just looking for very broad ideas. All right, guys, what do we have? Who wants to share one of their ideas? Just raise your hand. You look like you're really ready to share, Ruth. Can you tell me what you got? Okay. Yeah. I think a board game, and that was just something the student came up with. That's how it's not on the list. But I think a board game would be nice. And you could come up with all sorts of cool things, like takes on board games. All right. What else? Who has a good idea? Yeah, David? Okay. Okay. Would you do like a paper or a presentation or a video or? Okay. Like a YouTube type thing? Yeah. Okay, that would be great. Okay. That'd be great. That'd be a great topic. Huh? What is that? Oh yeah, my wife did that. She had an injury. They did that part. Yeah, that would be excellent topic. Any of those 3 topics would be excellent. And you could do an array of things, like you could just write a paper, or you could do an in-class presentation, like a PowerPoint kind of deal, and present it to the class. Or you could even do a video, which, with your permission, I'd show to the class. If you didn't want to, that'd be fine too. But if you put it on YouTube, like the whole world's going to see, right? So what else? These are great ideas. What else? Yeah, definitely. Okay. Okay. Yeah. Okay. Yeah, that would be great. Uh-huh. So she said determining the buoyancy of like ice, for example, in water, maybe developing an experiment or a presentation or something along those lines, and then also the flow of fluids, how to get fluids to flow without what? Without pouring it, yeah. So having pressure differentials, yeah. There's some great ideas for that on the internet too, like the length of a straw. What's the appropriate length of a straw, and how does the straw work? That's moving fluids around. What else? A couple more? These are great ideas. Yeah, it's Therion, right? Is it Therion? Okay. Oh, that's a good idea. So how different noises sound in one ear versus the other? Uh-huh. It's different, yeah. So she said, like, for example, if you're at a rock concert, I don't know if y'all go to rock concerts, but if you're standing next to the big speakers, how this ear, if you're standing right next to the speaker, is impacted differently from this ear. That would be great. I don't know that we're going to get to sound. That's okay. Like, if it's on the syllabus, then those topics are up for grabs. All right, one more really great idea. Yeah, Lucas?
Was thinking about the exercise physiology on this big object.
Okay. The exercise physiology of how much force it'll take to move an object. We're going to cover that a bit when we get into torques. So like the force that muscles exert. Okay. Your book has quite a bit on it as well. All right, those are all really good ideas. Listen, on February 14th, I'm going to expect a paragraph from each of you describing what you intend to do. You don't have to have all the details worked out, but I just want to have you thinking about it so that you're not doing it in the very last minute. So I'll need a proposal. That's worth a certain portion of your grade. It's on the rubric. You can work in groups. Do y'all remember, did I say 3 or 4? Up to 4? That is what it said? I'll find out. Okay, yeah, up to 4. No more than 4, though, please, okay? And if you have a group, each person has to have their duties outlined on the timesheet. All right? I expect about 5 hours for this. I think, it's worth 2 quizzes. You know that? It's worth 200 points. So I think 5 hours is a reasonable expectation. I don't want garbage turned in. I want good stuff. All right? That sound great? All right, good. Guys, I don't know if y'all know this, but I have like this Madonna headset and this Madonna headset. So I'm trying out a new recording thing, and hopefully I'll get better sound. It's a Bluetooth headset that you see people walking around with. They're talking on their cell phones. So we'll see. After today, I'll let you know how it works. All right, let's move on into Chapter 2. Chapter 2 is on motion. On motion, you do have homework assignment for this chapter. A good way to study for the test is to work the homework. I would go ahead and start on that. You can go ahead and start on it this week. Likely the quiz on Thursday will just be chapters 1 and 2. Let me see what chapter 3 is. The chapter 3 is on force. Likely it'll just be chapters 1 and 2. It'll be about 15-ish multiple choice questions. Similar difficulty to what you saw in the practice quiz, but it will include chapter 2. And some of those will come almost directly from the homework, all right, from those homework problems. Let's see. Chapter 2 is on motion. within motion, we have the study of kinematics. Kinematics. And kinematics is just, well, it's the study of motion. The root of this word, kine, means motion, right? Like kinesiology, kinetic energy, stuff like that. Now, a lot of what we know about kinematics today wasn't known prior to this, but Galileo and Newton both laid out the description of motion. So Galileo, he lived from 1564. You don't have to know these dates, but giving you to them for some reference, to 1642. And Newton was born right after Galileo died. So he was 1642 to 1727. All right, so they laid out the mathematical and the theoretical. That is, why do things move the way that they move? Description of motion. You know, any physics course includes a study of kinematics, and our study of kinematics will be fairly simple, but we're still going to look at all the various things that describe the way that things move. We'll look at their position or their distance that they travel. We'll look at the velocity or the speed, and then we'll also look at the acceleration. That is, how does the velocity change? In order to understand the physical world, you have to know how things move in it, right? And kinematics is really just a way to describe how things move. So it's important in a variety of realms, anywhere from like the simplest of things to even the most complicated, like say wireless communications or whatever. All right, so when we're talking about motion, we'll have a couple of different things that we will have to describe. The first is time. And of course, we already know the units for time. What are they? Right, the SI unit for time is in seconds. We usually call time a lowercase t. Sometimes you'll see an uppercase t, but usually it's lowercase. And usually, we're only concerned with a change in time. That is how much time has elapsed between one event to another event. And we'll call this change in time delta, as in, I don't know. Is there a Greek organization on campus with a delta? Delta zeta, yes, thank you. I knew there was one. So as in delta zeta. Delta means, in mathematical terms, is there a delta zeta? No, in this class. Okay, I'm sorry. What's your name? Aaron? Okay. So delta means a change in something. And so if we talk about a change in time, it's going to be t final minus t initial. So what's the difference from the beginning time to the ending time? I'll just abbreviate this TF minus TI. We use that delta quite a bit. Now, when we're talking about physical quantities, we're going to have two separate quantities, two separate types of quantities. One is called a scalar quantity, and then one is called a vector quantity. Now, time in particular, scalar quantities do not have any direction attached to them, and vector quantities do have a direction attached to them. I'll write that down in just a minute. What is time? Is it a scalar or a vector quantity? Does it have a direction attached to it? No, that's right, Danielle. It doesn't have a direction attached to it. You might think, well, time goes in one direction, but we don't think of it in the same way as having like a spatial direction. That is, is it moving north of east, or is it moving south, or is it moving up or down? In order to be a vector quantity, it has to have that sort of spatial direction. So time is a scalar quantity. And that means that it has no direction. It's a quantity that has no direction. All right? Can I go down from here to the next page? All right. Now, displacement, on the other hand, this is going to be we're going to use the variable s for displacement, and it's going to equal the final position minus the initial position. So see, I'll just write that out in words. The final position minus the initial position. All right, it's measured in units of what? What's the unit? Is meters, right. So we measure it in units of meters. And displacement is what type of quantity do you think? Is it a scalar quantity, which has no direction, or is it a vector quantity, which does have direction? What do y'all think? What do you think? Okay, what's your name again? I forget. Andrea. Andrea, it is a vector quantity. Very good. So displacement is a vector quantity. And that means that it has direction. And I'm going to go forward and say also that it also has magnitude. All right? Magnitude is just the amount. So for example, let's say that I'm here. All right, I'm going to call to the right positive. All right? I'm going to call this my initial position. It's going to be 0 right here. And then I'm going to step 1 meter, 2 meters to the right. What has been my displacement? I went from 0 to 2. So what has been my displacement? All right, it's been 2. In fact, it's been positive 2 meters. All right, positive 2 meters. The positive says that I've moved from 0 to the right 2 meters. All right, what if I start at this point, which I'll call 0, and then I move 1, 2 meters in this direction? What has been my displacement? Negative 2. And if I think about it's my final position minus my initial position, my final position right here is negative 2 meters. That's my final position, is negative 2, because I moved 2 meters to the left. And my initial position was 0. So negative 2 minus 0 is negative 2. All right? So this displacement has direction and magnitude, and that direction is given generally by the sign. I'll show you some examples right now. Let's say that I have a car. I have a car, and it moves from a position of 0 meters, and it travels over here to S equal 10 meters. All right, what is my displacement? It's going to be 10, which is my final position, minus 0, which is 10 meters. All right, but what if instead my car starts here? That's not a very good car, I'm sorry. That's pretty terrible. And then we'll call this 0 meters, but then it moves over here. To say a position of negative 5 meters. What is my displacement in this case? It's negative 5. So it's going to be S equal negative 5 minus 0, which is equal to negative 5 meters. All right, so that displacement has both direction and magnitude. Let's say, for example, I'll have a clip for you. I'll show it to you. I'm going to come away from this little clip to show you. All right, so we had going around, how long is a horse track? Y'all know? I think it's a mile. Am I right about that? I don't know. It doesn't really matter, does it? I have a horse track. And I have this horse that travels around it. Oop, 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 oop. He travels around the track, and he comes back in a certain amount of time. What is my displacement for this horse? What's the displacement for the horse? Is 0, right, because he has the same initial and final position. So he starts at, even though he's traveled a mile, his displacement is going to equal his final position, which is going to be 0, minus his initial position, which is 0. So even though he's traveled a mile, even though he's traveled a mile, his displacement is 0 meters. All right? It's a vector quantity. So it's only dependent upon the initial and the final position. Now we'll also talk about the distance that an object travels. And the distance is a scalar quantity. And this is what we usually use when we talk about traveled distances, is the distance. It's a scalar quantity. It's not dependent upon the initial and final position. It's just the total distance traveled. So for example, what was Seabiscuit's distance that he covered? A mile, right. Even though he started and finished at the same point, and his displacement was 0, the distance that he's traveled is a mile. So for example, in this case, I'll call my distance D, was 1 mile, or whatever it is that a horse track is. Displacement is a vector quantity. Distance is what type of quantity? Scalar quantity, right. All right. So let's look at speed and velocity. Then we'll work through some examples, and we'll do a little activity. David? Yeah? That's right. What are some scalar quantities? We've listed one, time. What are some other scalar quantities that have no direction? They measure some physical quantity, but they don't have a direction. What is it? Okay, mass is one. Somebody give me another one. Time, mass. Volume is a scalar quantity, right? Volume doesn't have a direction. It's a measurement of length cubed, but it doesn't have a direction. Area can also fall in that. What's your name? Rachel. All right. Another scalar quantity. Okay, charge. We'll get into charge at the end of the semester, but charge is also a scalar quantity. And then vector quantities are largely going to include displacement, velocity, acceleration, and forces, which we'll talk about in the next chapter. Scalar quantities don't have direction. Vector quantities do have direction. Let me write that back up here. So some examples, I'll just write it over here to the side. Some examples of scalar quantities: time, mass, volume, area, and charge. Those are all examples of scalar quantities. If you want to go and write down the vector quantities, we're going to deal with them, but just sort of to have them in the same place. Vector quantities include displacement, velocity, acceleration, and force. There are some other vector quantities, but these are largely the ones that we'll deal with. Displacement, velocity, acceleration, and force. All right. On the quiz, I could ask you a question to differentiate between what is a vector, what is a scalar quantity. Either just by definition, that is, scalar quantities don't have direction, vector quantities do, or I could give you a certain measurement and ask you, is this a vector or a scalar quantity? For example, is time a vector or a scalar quantity? And of course, you'd all say scalar, right? All right, good. All right, so let's look at speed and velocity. These are closely related. One is a vector quantity. One is a scalar quantity. They describe how quickly something is moving. or slowly, however it may be. Speed is a scalar quantity. Velocity is a vector quantity. Typically, the SI unit for both of these are going to be in meters per second, but we use all sorts of things to measure speed, right? Typically, what do we use to measure speed? We use miles per hour, like in our car. What does your car measure? Does your car measure speed or velocity? What does your car measure, speed or velocity? What do you think, Joel? Okay, you guess speed. Do y'all agree? Yeah, it measures speed, right? Because it has no direction information. Your car has no idea whether you're moving in a northerly direction or a southerly direction, so it measures speed. Does it measure distance or displacement, your car? Your little odometer on the car, distance or distance, right? If it measured displacement, every time you returned home, your odometer would read 0 miles, right? Because it would go back to the initial position. Obviously, that doesn't happen. All right, so speed is a scalar, velocity is a vector. The SI unit is meters per second, but in general, we use a distance per unit time. Now, we'll talk about average velocity. There are several sort of definitions. Average velocity. And average velocity is the change in displacement over the change in time. Delta S over delta T. This is our displacement over time. So we want to know, on average, as an object travels over a certain distance for a certain amount of time, what is its velocity? We'll write this in equation form. It'll be V with a bar over it is equal to delta S over delta T. And just to remember, delta means a change in something. Change in S, change in T. It just means how is something changing, our final minus our initial. All right, so let's do an example. This one is actually in your book, but it says a commuter is a person in a car, drives 6 kilometers east in 15 minutes. What is his average velocity in kilometers per hour? All right, y'all take a couple minutes and try to work that. 6 kilometers east in 15 minutes. What is his average velocity in kilometers per hour? So not only are you going to have to calculate his average velocity, but you're also going to have to convert it into kilometers per hour. Or a trick might be to go ahead and convert his time into hours and then do the calculation. Might make it a little easier for you. Because everybody knows how much 15 minutes is in hours, right? Y'all know that, right? Quarter hour? Yeah. Y'all are doing that. I'm going to work on your names a little bit. See, it's Lindsay, right? Lindsay? Sam? What's your name? Kelsey. David and Tyler. And your, what's your name? Shelly. That's Joe, right? Joe. Kaylee? Is that right? Kaylee? Alyssa and Joel, right? No, Ryan. Ryan. What we got? What I got the answer? Okay, what you got? All right, 24 kilometers per hour. I'll write it on the board in just a second. What is the direction for this average velocity? Because 24 kilometers per hour, that tells me the magnitude, but that's not the direction. What is the direction? What is it? Just east. So it's 24 kilometers per hour to the east. Two different ways that you could do this mathematically. You could say the average velocity is delta S over delta T. That's going to be, we said 6 kilometers over 15 minutes. And then you could do your unit conversion. You could say in 1 hour there are 60 minutes. And then that would give you 24 kilometers per hour. Or you could say 6 kilometers over 0.25 hours. That's a quarter of an hour. And that would also give you 24. 6 kilometers over 1/4. That's 6 times 4. 24 kilometers per hour. All right. That example is in your book. There are also several other examples. The direction is also very important. This is to the east. And that was stated in the problem, that it's to the east. All right. I want to try something. Never done this. So I'm going to need some helpers. Let me show you what we're going to do. This is called a constant velocity car. That's just a fancy way of saying that if I turn it on, it travels at the same speed constantly, that it doesn't change speed. Some cars will speed up or slow down, but this one travels at the same speed. I want to measure what is its velocity at a given time, and then also what is its average velocity. All right, so what I want y'all to do, I'm going to need 6 people, and I'm going to write it on the board, show you what we're going to do. Up here I have a piece of string that's laid out, and on the string there are blue pieces of tape that mark out 2-meter increments. 2, 4, 6, 8, 10. It's 10 meters in length. So what I'm going to need is I'm going to need people to stand at each of these pieces of tape. And we're going to let this car travel along the piece of tape. And each time the car, this person is going to start their timer, and they're going to measure the time to get from there to there. All right, so I'll have a person that's standing at this piece of tape, and the car will start. They'll start their stopwatch, and then when the car gets to that piece of tape, they'll stop their stopwatch. Is that clear? I want the time to get from here to that next piece of tape, to travel 2 meters. And then when the car gets here, the next person is going to start their stopwatch, and then they'll stop it when it gets over there. Same here, here, and here, and down there. So I'm going to need 5 people to do that. I'll call you up in just a second. And then I'm going to need a 6th person, and they're going to measure the time for it to get from here all the way down to here, delta t. And what we want to do is we want to look at, well, how does the velocity over a 2-meter increment change for the velocity over the whole 10-meter increment? How do you think they're going to differ? Which one is going to be larger, you think? The velocity, the average velocity over the 10 meters, or the average velocity over the 2-meter increment? Okay, over the 10 meters, you think? I think that's the general consent. I need 5 people. And, I have 3 stopwatches, but they're not very good. But I thought most of y'all are athletic training majors, right? Y'all have stopwatches on your watch? How many of you do have stopwatches that want to do this? Huh? Or your iPhone or whatever has a stopwatch. I need 6 people. All right. Not everybody wants. All right, Lucas. Demi. Okay, you can borrow one of mine. All right, somebody wants to give you theirs. Rachel, right? Is it Rachel? What's your name? Deshawn. Deshawn or Deshauna? Deshawn. All right. So folks, listen, y'all can stand here. Find a piece of tape. There's a piece, just stand down at the bottom. Demi, you can stay down on the carpet. You need a piece of, there's a person here, a person here, person here. I need two people. Deshaun, you can, we can go up on the stage. You can be that sixth person, all right? So you're going to be the time taker for the, no, Demi, I also need you right here. Need one more person. Need 6 people. Thank you, Danielle. David, if you could come down here.
Oh, sorry.
It's just me and Deshaun up here. Nobody else. All right, did you get a stopwatch? All right, is everybody clear on what they're doing? Lucas, you're going to start it when it passes that blue tape, and then you'll stop it when it gets to David, to this blue tape. David, you'll start it, and then you'll stop it when it gets here. Then Danielle, you'll start it, and you'll stop it when it gets here. Rachel, you'll start it here, and then you'll stop it when it gets here. I need one more person, I guess. I don't know how my, yes, he's measuring. I need one more person, please, with a stopwatch. Joel, you got it? All right, come on. You have a stopwatch? Good. So Joel, you'll start it when it gets here, and then you'll stop it when it gets here. Is that right? No, I'm sorry, Joel. We don't need you. Come on down here. And then you'll start it here, and then stop it when it gets there. And then Deshaun, you're going to start it. I'll like raise my hand up. When I put it down, you'll start. And then when it reaches you, you'll stop. All right? Y'all ready? Is this exciting? Okay. You're going to start it when it gets here. When it passes you, that's when you start it. When it reaches the next person, that's when you stop it. All right, I'm going to give it a little bit of a head start so it can sort of get into place. I want to be like one of those, what's it called? The with the ice, the thing where they get the thing going. You know what I'm talking about in the Olympics? The shuffling. What's that called? Curling? Curling. I want to be like that guy. I'm going to try to keep it in a straight line. All right. When it passes your tape, you start it. Deshaun, go. And you stop right here, Deshaun and Demi both stop here. All right, good job. All right, keep your time. You're going to report them to me. Yeah, you need an alignment in this thing, right? My dad used to work in a tire shop. He's retired. So we used to, when I was a little kid, did y'all care? Y'all care, right? When I was a kid, we, my brothers and I, we all worked in the tire shop, like starting at like 12 or whatever, or 11 even. We just sweep and stuff. But the other guys in the tire shop would always make fun of us because we'd call out, "Daddy, Daddy, Daddy." We were just little kids. Let's see. Daddy. Let me pull up Excel. All right. So this is going to be my time. Who was my first one? Lucas, what you got? 8.35. David? Danielle? 7.8. There's going to be some scatter. 7.5. 7.3. And Deshaun, what you got? 41.10. All right. Y'all can go sit down. Thank you. All right, so this was our total time. Our total distance was 10 meters. For each of these, what is the distance or the displacement? 2 meters for each of them. All right, I'm going to calculate what is the average velocity. Let me blow all this up so y'all can see it better. All right, so my average velocity is going to be the distance divided by the time. So I'm getting about 0.2 meters per second. Let me get a few more sig figs here. All right. That's pretty good, I think. So what do you think we should see? How should the velocity change for each of the 2-meter increments as it goes along? It shouldn't change. My car should be a constant velocity. It seems like it's increasing, but I'm not sure that it is. Maybe it is. Maybe something happening to the batteries and it is speeding up. But I think within our error, our uncertainty is actually pretty good, that we just go from about 0.25, 24 to 27. And then our average velocity over the total length of the string should also be the same, because the velocity is not changing as it goes along. So the velocity that I have for a 2-meter increment should be the same as the velocity that I have over the whole thing, because it's not changing. Let me show you one thing. We're going to get into graphing in just a little bit. So let me make a quick plot of this. I want to make a plot of what is the distance versus time, the elapsed time. All right, I want to make a plot of the distance versus the elapsed time. What do you think that's going to look like if I make a plot of the distance versus elapsed time? Or you think it's going to look like that? Do you think it'll be curved or straight? Let's just see. Think about in your mind, what should it look like? So in order to do this, I'm going to get rid of this average velocity. I'm going to need my total elapsed time. So here, for example, it's going to equal 8.4. And here, it's going to equal this plus this. That's my total elapsed time, right? This is my elapsed. And this will be my distance. I'm going to move it over here. Oh, I also need to put in, this is my total distance covered. All right, so this is total distance over total time. That's a pretty darn good graph, actually. It's a straight line, okay? We'll look at the slope in a little bit. Is this a positive or a negative slope? This is a positive slope. I'll show you some examples of what's a negative slope. But here I have something that's moving at a positive slope. That means that the velocity is positive. Let me write that. So this has a positive slope. That means that the velocity is positive, because the slope of a d versus t graph gives the velocity. The slope of a v versus t graph gives the velocity. And since it has a positive slope, it has a positive velocity. We'll do some more examples of this in just a bit, but I just want to sort of introduce it right now. I can also calculate the quantity of the slope. You all know how to calculate slope? Rise over run? I certainly did that. I'm pretty sure you did in high school. So I can determine my, my slope. In Excel, you can do this automatically. Let me just see what our slope is. Okay, it tells me that my slope is 0.26. 0.26. Y'all remember the range that we had for the average velocities? They went from about 0.24 to about 0.27. So when we graph the data, it tells us that our velocity over the whole range of time was 0.26. It's pretty darn good data, guys. That's very difficult to time those. That's pretty darn good data, though. All right? So good work. We'll see more examples of this later. I just want to sort of introduce it right now. Y'all follow me, though, what I'm doing? Okay. Is this useful, this thing? Yeah. We'll do another one in just a bit. It'll be a little more difficult. We'll get some different people to do it. All right. Let's see. Where was I? Can also look at average acceleration. So that was average velocity. We also need to define what is our average acceleration. Our average acceleration is defined as delta V over delta T. It's our change in our velocity over our change in time. This tells me how quickly I'm speeding up or how quickly I'm slowing down, all right? For example, in your car, how would you speed up? How would you increase your velocity? Right, you would increase the speed, but you would press what? The accelerator. That's why they call it the accelerator. You ever thought of that? Because it causes you to accelerate, to speed up, all right? So our average acceleration just describes how our velocity is changing. Is our velocity increasing at a large rate, or is it decreasing? Now, acceleration is a vector quantity. It has magnitude and direction. It has magnitude and direction. So tell me, what is my acceleration in these cases? You ready? What is my acceleration? What's my acceleration roughly? Huh? 2.9? No. What am I doing? I'm walking at a constant what? Hey, y'all, it's a pretty good walk for me, huh? What's my acceleration? It's 0. I'm not speeding up. I'm not slowing down or whatever. All right. How about now? Let's see. That's right for y'all. Is my acceleration 0 or non-zero? Is it positive or negative? Positive, right. Let's try it now. All ready? What was my acceleration? Is it 0 or non-zero? Non-zero. Is it positive or negative? Ah, good. It's negative. Even though I'm speeding up, it's negative because the negative gives what? It gives the direction. Right. So if I'm moving in the negative direction, even if I'm speeding up, my acceleration is still negative. So the negative doesn't necessarily mean that you're slowing down. All right? We'll see more of that later when we get into free fall. Has magnitude and direction. Let me just try to write that in words. Acceleration can be negative. The negative gives the direction. And in physics and in the world, the larger world, we live in this right-handed world. Like mathematically, we use right-handed coordinate system. And that means that left is negative. And then typically we take up to be positive and down to be negative. Left and down are negative. All right, left and down are negative. Also, typically, south, I think you encountered this in your homework a bit, south and west are negative as well. All right, south and west. West is sort of to the left, right, if you look on a map, and south is down if you look on a map. So left and down, west and south are both considered negative. And then the converse of that, right and up is positive. North and east is also positive. All right. All right. Let's do an example. This is an example from your book. It's example 2.2. It says, what is the acceleration of a car that goes from 0 to 90 kilometers per hour in 15 seconds? And I want to know, what is it in meters per second squared? What is it in meters per second squared? What is it in meters per second squared? So go ahead and practice converting that 90 kilometers per hour to meters per second, and then you can do this calculation. Remember, in a kilometer, there are how many meters? There are 1,000 meters in a kilometer, and in an hour, there are 3,600 seconds. It's good practice because you will see some unit conversions next week. Go ahead and convert that to meters per second, and then calculate the average acceleration. Let's give you a couple minutes, and I'll step in. Anybody have this in meters per second yet? Okay, that's 90,000 meters per hour, yeah. What was it in meters per second? Anybody know? If not, that's okay. Tyler, you have it? 25 what? It is 25 meters per second. Very good. Let me show you. Yeah, David, you had not done the hour conversion. So I convert my kilometers to meters, or you can use that whole thing about the monkeys eating something and dying. Monkeys, is that what it was? Yeah, the dirty monkeys. Yes, that's what. Okay. All right. It's what? Okay. Right. Right. Okay. All right, I got you. Thank you. All right, in 1 hour, there are 3,600 seconds. And if you do this, it's 25 meters per second. And now I want to know the average acceleration. It's just delta V over delta T. It goes from 25 meters per second is its final minus 0. That was its initial. Divided by 15 seconds. Let's see, I don't have that. What is that? 5 over 3, 1.7. Is that right? Is that right, 1.7? 1.67? Yeah? That's right. Yes. Okay, 1.7 meters per second squared. All right? Yeah. What's the direction for this acceleration? Oh, I didn't say, actually. In the problem, if you look at the example, it says that the car is traveling to the west. And so the direction of the acceleration is in the same direction, to the west. All right? Our motion problems are going to be fairly straightforward. You can see in the homework, and they'll be similar to the examples that we're working. Let's see. I don't think we need to do this at all. Let's just do another example. Well, no, let me show you. So solving these motion problems will require a little bit of algebra, not very much. So I've already said that the velocity is equal to the distance over the time. So what if I'm given the velocity and I'm given the time and I want to figure out what is the distance that's covered? How would I solve this for S? What's that? Right, I multiply both sides by time. I think y'all are probably okay on this, right? On sort of simple algebra? If you're not, guys, then please come see me, because if you get sort of left behind now, that it'll be difficult to catch up. So if I multiply both sides by time, my time over here cancels out, and then I have an expression for S is equal to V over T. So we can take these equations that we're given and then solve for other things. All right. So like, for example, let me give you an example. How long will it take a runner to run 1,500 meters if he has an average speed is 5.4 meters per second? All right. So I have this sort of basic kinematics equation, and I'll show you a couple other equations probably next time. But I have this basic kinematics equation, and that's two of the quantities. I want you to solve for the third unknown quantity. The unknown quantity here is I want to know the time. All right. So go ahead and solve for the time. This is example 2.3 in your book, by the way, if you want to follow along in your book. But I prefer you do it on your own. You know when you get a number. You have a number? What's your name in the white? You have a number? No? Okay, not yet. What you got, Joe? That's what I got too, 278. Yeah, so if I want to solve for time, I can take this S equals V over T, or V times T rather. I just divide both sides by V, and then I get an expression for T, and my T is equal to S over V, and then it's just a matter of substituting in the right quantities. 1,500 meters over 5.4 meters per second, and that gives me 278 seconds. All right. There are no math prereqs for this course, so our math will be fairly simple, but we will do some math, and especially in kinematics and solving for different quantities. Next time, I want to show you a video now, but next time we'll, let's see, we have 10 minutes left, is that right? Yeah, next time we'll get into some slightly more complicated problems. If you want to read ahead, just go ahead and read Chapter 2, but I would certainly go ahead and start working on the homework for Chapter 1, all right, because you can probably wrap up a lot of that right now. I have a little video. This is about